Thanks very much. Well, so I wanted to talk about some big ideas and how they translate into practical technology. And so I'll talk about some things around computation, around knowledge. They really all come from three pillars of development that I've been involved in for the last 30 years or so, kind of steadily building up. Those three pillars are basically three large projects that I've done. One is Mathematica, a language that I'll talk about in a bit that is about to be 25 years old. Another is a new kind of science, which is kind of a direction in basic science that I've worked on for a long time. And a third is Wolfram Alpha, which is a fairly new development and a very, very ambitious one, kind of probably the most consumer-visible aspect of our stack of technology. So the goal of Wolfram Alpha is, it's sort of it was a project one might consider impossible. The goal was to kind of take all the knowledge that's been accumulated in our civilization and make it computable. So that, in a sense, if there's a question that can in principle be answered on the basis of knowledge that has been accumulated by our civilization, we should make it automatic to be able to answer that question. If there's some expert that you can find somewhere who could answer a question for you, automate that process. Make it kind of something that's accessible to anyone, anywhere. So, at first, it took me many decades, actually, to decide that something like Wolfram Alpha would actually be possible. Let's see whether I can get it to... OK, less exciting. We'll just have some... we'll just use a canned video here rather than a live demo. Live demos are much more fun. But anyway, so let me talk about kind of the concept of Wolfram Alpha. The concept is... you ask it some question that can be answered on the basis of sort of known knowledge, and it will try automatically to answer that question. So there are really three big components to making something like this work. The first is to be able to have all this data about the world, and so that what we've been concerned with doing is sort of finding all of the primary sources of data that exist in the world across thousands of different domains and so on, and then being able to make that data computable in the sense that one sets it up so that it's possible to not just look up a piece of data, but actually be able to do computations from that data. So the first step is ingest all these different domains of human knowledge. The second step is typically what people want to know is not just one little piece of data from that database. They want to work out the answer to some question that can be answered from that data. And so in addition to having all this data, we have to build in the kind of methods and models and algorithms and so on that have been developed in science and engineering and financial analysis and all these kinds of areas, and set those up so that they can be used on all this data that exists. Third component is, OK, so we can compute all these things. We have all this data about all these different kinds of areas. How do humans actually ask the questions? And it's a broad enough area of interest that sort of the only language that is going to work for that is human natural language. And sort of been a long-term problem to see to what extent we can make computers understand human natural language. It's kind of a 50-year story. But we've had two tremendous advantages in being able to actually understand human natural language. The first is that we have a huge amount of knowledge built into our system. So when humans actually understand what each other say, we use a lot of that kind of knowledge about the world. For the first time in Wolfram Alpha, we're doing natural language understanding with a background of large amounts of actual knowledge, and that's a tremendous advantage. The second thing is that we're solving a slightly different problem than people have been interested in before. We have kind of little fragments of text, and we want to map those fragments of text onto something from which we can compute answers. That's a little different from sort of the standard case of understand this giant corpus of text and try and sort of grind it up for computation. I should say that you might think, well, why can't you just forage all this knowledge from the web? That's simply an unworkable thing because the web is just not a systematic enough source of knowledge to do this kind of thing. And by now, in fact, the actual data that exists inside Wolfram Alpha is somewhat bigger than the complete text content of the web. So even if everything that was on the web was really systematic data, and it's far from that, it wouldn't be as much as what we now have built into Wolfram Alpha. So there are all sorts of things about Wolfram Alpha that I would have loved to show you, but I'm not going to be able to because we can't communicate with the outside world here. The Wolfram Alpha is showing up in all kinds of places. It's the basis for the knowledge component of Siri. And if you scroll all the way down to the bottom of Siri outputs, you'll see a nice Wolfram Alpha logo there. We think it should be bigger, but we're happy that about 3/4 of the ads that Apple runs about Siri are our outputs. So that's at least complementary. And it's also used in Samsung products and a bunch of other different mobile applications and so on, as well as on the web, and the large number of different startups and others who are making use of the Wolfram Alpha API to kind of deliver knowledge into applications that they're developing. One of the directions for all of this is not only to have textual input, but to have input that's things like images, data, and so on, being able to mix information about some spreadsheet that's uploaded with actual sort of general knowledge about the world and so on, and being able to automatically compute things from that. Another thing that's kind of been a big development the last couple of years is the corporate versions of Wolfram Alpha, kind of making custom versions of Wolfram Alpha for large organizations, being able to sort of go from the kind of the pure big data to actual sort of big knowledge, and being able to take the large amounts of data that exist in large organizations and actually be able to query them and make use of them using natural language kinds of inputs. Another feature of Wolfram Alpha that you're probably seeing from some of these outputs is that kind of the objective is not only to answer a question, but also to generate automatically a whole report about about the knowledge that's being dealt with. There's an awful lot of math-related. OK, there's a non-math-related question there. OK. It's more fun to see this in real life. You can try it on any web browser. Just go to wolframalpha.com. It's pretty widely used these days. I think that the kind of it's used by lots of professional people. It's used by a certain number of tourists, so to speak. It's one very central core market at this point is students who are kind of big consumers of knowledge and computation and so on. So in the US now, I think about 1/3 of all kind of high school and college students use Wolfram Alpha at least once a week, which we consider to be a fairly encouraging point to have reached. So anyway, Wolfram Alpha is one kind of pillar of our technology world. Another one is Mathematica, and so as I mentioned, Mathematica is now it's about to be 25 years old. It's about to celebrate its 25th anniversary, and let me show you a little bit about it. So the idea of Mathematica is to provide a language and an environment to do any kind of algorithmic work that one wants to do. So we can start off with something very simple. We could say, plot a graph or something like this. We could say, set this up so that we can manipulate that plot. We could put in something like this and say, make this go from 1 to 10. It'll sort of automatically figure out how to create a little user interface from that, make a result like this. We could say something like, here, how about we take another, let's take another kind of input. How about, let's see what happens if I do this. So let's say I get an image here. Let's see if this works. There we go. Oh, OK, there's a good image. So we can use, Mathematica is a symbolic language which can kind of deal with any kind of object as data. So you can deal with an image as data. So for example, we can go here and we can say, detect edges in this image, and now that's we'll have edge detection of you guys there. And if we go and say something like dynamically edge detect the current image, we could get. Let's see if this works. Write some code here, and if I go and wave my hand in front, it should all work nicely. So you can do. So this is kind of a big world. Now, one thing that unfortunately won't work here because we don't have network connectivity. One of the things that's interesting is combining this very systematic language in Mathematica with Wolfram Alpha, so that I can say things like just plot a sine curve, or do some image computation or something, and I can basically use natural language as the input. And then have Wolfram Alpha figure out how to convert that into a precise programming language statement. So Mathematica gets used these days in most organizations that have a real R&D department use Mathematica in some way or another. It's also pretty universally used in universities for both education and research purposes. I actually think the time has really come to greatly broaden the ways that this basic piece of technology can be used. Kind of our goal with Mathematica has been to sort of build into the system any kind of lumps of computational work that are well-defined and that can kind of fit together. There's sort of been a big effort to set things up so that it remains a coherent system where all the pieces can be kind of connected to each other. Another kind of principle is that it should be as automatic as possible, in the sense that while there may be hundreds of different possible algorithms for doing some particular operation, we want to figure out automatically which of those algorithms to use in a particular case, so that the user just sort of has to define the goal that they want to achieve, and the system will then figure out how to actually achieve that goal using the algorithms that it knows about. Well, so the things that the thing that we're doing right now actually is taking Mathematica and kind of taking the language component of Mathematica, the Wolfram language, and making that something that is much more broadly deployable in the world. It's something where it's sort of remarkable how quickly one can actually get some significant algorithmic functionality up and running in this language. The challenge is to make that language as widely available as possible. So there are a variety of different deployments that are coming. One that I would love to show you, but I'm not going to be able to, is the cloud version of the language, kind of a programming cloud where you can just write a few lines of Wolfram language code and then immediately be able to deploy that code as something that can be called by, for example, a website or some other application or whatever else, to sort of instantly create an API that implements this particular piece of algorithmic functionality. So the idea is that one's able to take this language and use it in the cloud, on the desktop, on a server configuration, a private cloud, and so on. It's sort of a unique case where one can take something which can be implemented across all of those different kinds of deployments. I think the thing that is also true is that the language kind of scales from being the few lines of just the one-line thing that does something interesting to something like the whole Wolfram Alpha system, which is now about 15 million lines of Wolfram language code. Well, there's also mobile versions of this. So there's sort of mobile access to the language and to our engine, for example, on iOS. Things like Siri use the API that we have. There's also a technology we call CDF, the computable document format, which I again can't show you because it relies on being able to get data from the cloud. The CDF, kind of what's possible there is to make lots of, well, this is a very trivial example of CDF. Maybe I can make, let me make something slightly more interesting. How about I make, I don't know, let's say, something like this. So this isn't going to be too exciting either. I'll tell you what, I've got a better idea. Let's see. How about, no, okay, yeah, I've got an idea. And so this does. maybe that wasn't such a good idea. Oh, no. I know what I did wrong. There we go. So, in any case, we can, oh, that's okay. In any case, all sorts of different, well, okay, let me go on. I can probably improvise something here, but let's not try to do that. So another direction that's interesting with the Wolfram language and so on is sort of for the first time this year, it's possible to run this language in its kind of full form in embedded processors. So things like Raspberry Pi and so on, you can have this complete language running inside such a thing to be included in devices and so on. I should say sort of the philosophy of the Wolfram language is different from basically every other programming language in the sense that typically programming languages kind of provide a lot of sort of superstructure for handling the construction of programs, but when it comes to the actual raw computational capabilities, they're fairly close to the raw capabilities of the machine. In the Wolfram language, kind of the idea is to have large amounts of algorithmic capability built in an integrated way into the language. And that sort of allows different kinds of things to happen. Another characteristic of the language, again, let me see if this, if we're lucky, this has been cached and won't require accessing the network. But we're not lucky. Oh, well. The thing that's interesting about, no, something's there. Okay, let's see whether we can do. We'll have to hope that things happen to be in the cache. Okay, there we go. So maybe I can say something like this. So what I'm doing here is to make use of. There we go. That's kind of cool. And we could, for example, go and do all kinds of computations on this. But what's important here is that we have kind of knowledge-based computation going on. In addition to having lots of algorithms built into the language, there's also a large amount of knowledge built into the language. In fact, all of the knowledge that exists in Wolfram Alpha, covering all of these different domains, is all accessible to this language. And just to give a sense, I think I have, let me see. If we're lucky. No, we're not lucky. I was hoping that there would be something cached here that, let's see. Oh, okay, maybe it's working now. Okay. Wow, all right. That was a shame. Let's see if it's working now. No, it's still unbelievably slow. All right, never mind. In any case, this is just some sense of the kinds of knowledge domains that we're dealing with there. Well, okay, so this is really, so the sort of a question of so I've talked about embedded computation, kind of being able to get this whole stack of technology into an embedded device. There's also one thing that we've been doing a lot of work on is kind of connecting to devices of all kinds and sort of providing, with our technology, a kind of generic analytics platform for all different forms of sensors and devices and those kinds of things. I think one of the areas that's kind of fun that's come out of that is doing personal analytics. I've long been a sort of enthusiast of data. So, for example, I've been collecting data about myself for a long time. I realized somewhat to my embarrassment about a year ago that I'm probably the human who's collected more data about themselves than anybody else so far. So this is, for example, a dot for every piece of email that I've sent for the last 25 years. And shows all kinds of sleep patterns and other sorts of things. Or there's a dot for every keystroke I've typed for the last few years. And you can compute all kinds of things like the daily rhythm of when one's on average doing emails and phone calls and walking around and those kinds of things. It's kind of interesting to see this sort of this is the kind of data that one can easily get from sort of sensors, and one can imagine doing the same kinds of things with medical type sensors and so on, and developing a whole a whole technology around that. Most people haven't been collecting data like this. We actually set up a thing a few months ago to take people's, the sort of digital trail that people leave on Facebook and be able to generate personal analytics from that. Actually, one thing that we've very recently been doing that I might be able to show you here is to take anonymized data from Facebook and sort of do the data science of, from that using Wolfram language technology and so on, just taking, so there, for example, are a few social networks from data donors that we have. And you can look at all kinds of things, like you can look at how the number of friends that people have varies with age, for example, and for example, how the relationships that people have, you know, what fraction of people are single, married, and so on, varies with age. One thing that was a surprise to me, maybe I have that here, if we compare what you get from kind of what people report on Facebook with what the Census Bureau in the US actually gets from the real population, the results are surprisingly close. So you get a surprisingly good representation of actual society, so to speak, from what you see on Facebook. And there's, for example, there's the plot of kind of the motion of people according to where they say they come from versus where they say they're living now in Facebook. What's another? Oh, there's a few other networks. This one is kind of fun. This is looking at based on what people post on Facebook. This is looking for men and women as a function of their age, what the popularity of different topics is, and you can see all kinds of things about humans and life and so on, from school and university peaks when people are doing that and so on. People seem to get more interested in politics as they get older. Those types of things. So it's sort of interesting to see this kind of data science flow through, and this is something that's very straightforward to do with our kind of analytics platform. It's been an interesting exercise doing this. Actually, I've sort of become convinced that data science is an important component of kind of general education, and we've been involved a lot in education, and so one of the things we're actually doing now is to build sort of a framework for creating online courses using the Wolfram language as kind of the environment and the mechanism for people to be able to actually explore the concepts that are being discussed, as well as just listening to a presentation of them. I might mention, in a slightly different direction, I was going to mention before, did I completely run out of time?
No,
Yes.
go ahead.
I'm sorry, I'm trying to, well, maybe I should, let me mention a couple, okay, I will put up one slide that is about something I won't talk about in detail, but sort of one part of the kind of the world of Wolfram language and Mathematica, Wolfram Alpha, sort of a coming attraction. There's a product we have called System Modeler, which is used for large-scale systems engineering, used for things like simulating sort of all the components in a car or an airplane or something like that. There's sort of a very interesting thing that becomes possible when you connect that kind of large-scale systems simulation to Wolfram Alpha, where you get to kind of ask a question and then actually simulate how some very large system will behave to answer that question in real time. Maybe I should, I'll just mention one more thing, but won't go into it perhaps. So the reason that I kind of started building things like Mathematica was actually because I wanted to use it myself. And I've been interested a lot in basic science, and kind of the main direction that I've been interested in is sort of for the last 300 or so years, kind of there's been this idea that if you want to model the natural world, mathematics is kind of the raw material that you should use. The thing that I kind of started thinking about 30 years ago now was to sort of generalize something like mathematics and think about sort of the space of all possible rules for constructing what happens in the world. And the way to think about that is to think about sort of the computational universe of possible programs, and then to ask questions about, so what do different possible programs out there do? And sort of a big discovery is, if you look at very simple programs that are the equivalent of one line of code long, let's say, very different from the kinds of programs that we're used to writing as humans, Many of those programs do very simple things, but sort of a big discovery was that there are programs that, that instead behave in very complex ways. So, for example, this is sort of my all-time favorite, called Rule 30. It has this little program down at the bottom there, produces all this elaborate behavior. You can find lots of programs that, in this computational universe that do this kind of thing. This has been pretty important in sort of redefining the way that people think about making models for scientific purposes. A thing that's been exciting to me is using this sort of these discoveries about the computational universe as a source for technology, because basically what one's doing is mining this computational universe of programs and algorithms and so on for ones that are useful for particular technological purposes. So, you know, you might say, I want something that does a good kind of image processing with these characteristics, and then you go and search 1 trillion possible programs in this computational universe and find the one that optimally does that. What you end up with is a new way to do engineering, where instead of constructing things step by step, you're just going out and searching this kind of raw material of the computational universe to find a way to solve the technological problem. And this has been an approach, this kind of algorithm discovery mechanism has been something that's been pretty central to our development of technology, sort of made Wolfram Alpha possible. It's about to make possible a whole bunch of other applications of very different kinds of things, including things like medical diagnosis and so on, that are kind of coming attractions for this type of thing. And I'm really sorry about this network issue, not of my making, I have to say, so I'm afraid this has been a bit more disjointed than I would have liked, but I hope I managed to communicate at least a little bit of interesting stuff, and I'm happy if there's, I hope there's time for...
There's time for questions, that's the good thing. Thank you very much to start with.
Yes.
Needless to say, the apologies are from us to you for not providing you with a proper internet connection. We're very embarrassed by that. We do have some time for questions, and I'll start with people in the audience. Please do wave your hand or go to the microphone if you have specific questions. I think you probably...
Great, please.
Hello, microphone is working. Thank you for the great presentation. Actually, I have a question regarding how is the content curated? Because right. I mean, the content, there is a lot of evolution in the data and perception of people.
So I mean, you know, for us, there's kind of a pipeline that we've developed. So first thing is identify the best primary source for any domain of data. That's a non-trivial thing, because it turns out that there are sometimes many different sources for a different particular kind of data. Sometimes there appear to be many different sources, but actually all the data comes from one place. We actually run a data summit conference every year where we kind of collect the people who run many of the large data sources in lots of different domains. So we've done a lot of work on sort of interacting with primary providers of data. So first step is identify the best primary sources of data. Usually the actual ingestion of the raw data is very easy. The problem is to make that data computable, to really understand what the data is, to link it up in the right kinds of ways. My general principle about that has been, if there isn't an expert involved in that process, you will get it wrong. And so we have a fairly large number of in-house experts in lots of different domains. We're also kind of lucky that through our work in Mathematica and so on, we kind of know the world experts in a huge number of different areas and can reach them. And so typically, you know, we will have communicated with sort of the world experts in some particular domain as we try and build out that domain. It gets easier. You know, we've done a few thousand domains now. It gets easier to do the next domain when you have a few thousand domains already under your belt, although every new domain has some weird different feature that you've never seen before. And also, I think as we see all these different domains and can link them up and cross-test things and so on, we get more ambitious in what you can achieve in the next domain. So it stays being difficult all the way. But that's kind of the approach. We've developed this kind of mixture of lots of automation together with human processes that inject actual experts and so on for doing this data curation thing. It's a very, in a sense, it's a very, well, our company isn't based in Silicon Valley, but it's a very non-Silicon Valley approach because they're actual humans and actual experts involved in doing all of this. It's not something where we sort of turn loose a machine and it goes and figures it all out. I think all the time about, am I being stupid, and is there just some completely automated process for doing everything we do? I think the answer is no, but we only have to do this once, because we're progressively going through sort of the knowledge that our civilization has accumulated. We're progressively, being able to make it computable. Once that's done once, it's done. But it's a lot of work to do it. Thanks.
But the way I'm just a simple princess, I use Google all the time. I'm sure the Google people have called you. Do you see your company developing as some alternative to what we now use for search?
Well, it's a somewhat different approach. I mean, I've known Sergey Brin was...
It is, but they will call you anyway, right?
What's that?
They would call you anyway and say, okay, just be part of Google.
I mean, Sergey Brin was an intern at my company long before he started Google, so
look.
I do know these people. I think, kind of our approach is rather different. I mean, what we're doing is to say, let's compute fresh answers to questions that have never been asked before, as opposed to, let's take what happens to have been written down on the web and be able to sort of give pointers to that information.
Yeah.
So the web itself actually can be viewed as a data set, and you can then ask about computations from that data set, but that's sort of a different problem. What we're interested in, I mean, for example, in Wolfram Alpha on the web, for instance, the vast majority of questions that we get asked have never been asked before and don't show up anywhere on the web. So they're things that have to be sort of computed from scratch. It turns out that particularly in things like mobile environments, there's a higher pressure to get kind of just give me the answer. Don't just send me to a bunch of links. I just want the answer. And that's a place where the kind of thing we're doing is I think, of great interest. The other thing that sort of is emerging is not just give me knowledge, but also perform actions in the world on the basis of, for example, linguistic input and so on. So yes, it's a different approach. I mean, this is kind of the computational knowledge approach as opposed to the search for information approach.
Because I'm going to ask another one. Is there a question over there? Same question. Well, my question as well is, I mean, you know so much about, the computational world that you probably have a vision where we'll be in, let's say, 10 years. What will be completely different from what we do now? I mean, is it sort of more of the same, or will something else happen?
Lots of things will happen. I think that in lots of different domains. I mean, I think, one of the things that we'll see right now, knowledge delivery tends to be on demand. It will be much more preemptive in the sense that we'll know from personal analytics data, for example, what one is interested in, and one will be able to sort of preemptively deliver that knowledge on the basis of one's previous history and the particular environment one finds oneself in. So that, I think, will be one difference. That for us, for example, we've been building up all of this knowledge and so on, and the frustrating thing, in a sense, is that people don't know what to ask. So for us, once we can combine personal analytics with all of this knowledge, we get to tell people what we think they will want to know at a particular moment. Yeah. That's one thing. Another thing is sort of a general trend is more things will get automated. I mean, this is kind of the story of technology for thousands of years, is that first humans do things, they figure out how to do them, and then there gets to be an automated way to do them. I think the question that arises is, okay, so what's the ecosystem like between the humans and the machines and so on? And I think increasingly what you'll see is the humans are simply involved in defining what's the goal, what's the purpose that one's trying to achieve, and then it's up to the machines to figure out how that purpose should actually be achieved. Okay. So another area, just to mention one more thing, is we happen to be working on is automated medical diagnosis. It's sort of an interesting case where that's something that has traditionally been, it's pretty hard for humans to do medical diagnosis. They get it wrong all the time. And increasingly, it's an area where there's more and more specialization, and it's more and more difficult for somebody to be able to say, which specialty should be involved in this diagnosis or whatever. And so it's something where it's kind of an area where I think it's sort of ripe for automation, and there's also kind of the whole sensor-based medicine that's arriving. I could talk much more about this, but I think this is an area where we're going to see.
Unfortunately, we have to wrap up.
Okay.
Thank you so much.
My
it
pleasure.
has been an honor to have you here.